Okay, so today we're going to go over some of the background material in Fourier transforms that will be useful for understanding especially the second part of the course on MRI. So it's a small group, so feel free to stop me if you have any questions. Okay, so this is geared towards you. I have slides, but if you want me to stop for any reason, just let me know. So in the last supplementary session, we talked a little bit about, sort of how we represent signals and images. And if you remember from last time, we would represent things using weighted sums of delta functions, right? And so basically, we had, for example, this could be equal to like, delta of n plus delta of n minus 1 plus so on and so forth. Okay, so we just had weighted delta functions. So today we're going to sort of take a different view, and instead of using delta functions, we're going to represent signals as a sum of sinusoids. Initially we'll talk about sines and cosines, but we'll actually move fairly quickly to using what are called complex exponentials. And the reason for that is because actually when we do MRI, we actually impose complex exponentials in the body, and so that's actually a more natural way to think about it. Right? But here's an example. So for example, let's say this is a signal that you might see on your, like a radio signal, let's say. And it looks fairly complicated. And if you were just to look at this signal and represent it with numbers, you'd probably think you need many numbers to represent that signal. Okay? But it turns out you only need 3 numbers, or actually 6 numbers. You need to know these different frequencies. So each of these components has a different frequency. So this might be frequency 1, frequency 2, frequency 3, and then each of them will have an amplitude. So A1, A2, and A3. Okay? So this is actually just a sum of sinusoids with different amplitudes. All right? And then what we would say is the Fourier transform, we could just say is those amplitudes A1, A2, and A3. All right? So that's essentially the basic idea behind Fourier transforms in 1D. And so you might be familiar with that already from, say, physics or some other course you've taken. In 2D, which people are slightly less familiar with, what we have is actually sines and cosines. It can be in different directions. So we can have vertical stripes, we can have horizontal stripes, we can have diagonal stripes. And the idea is any image can be represented as a sum of these types of stripes. So this is a figure from the book, and here they're using U0 to represent the frequency in the x direction and V0 to represent the frequency in the y direction. Okay, so that's the convention they use, but a much more common convention, and the one we'll use, is instead of U0, we'll use Kx and Ky, okay, as the frequencies in the spatial frequency in the x direction and the y direction. And I think it's a lot easier to remember because Kx and Ky sort of tell you which direction it's in, whereas U and V don't really necessarily do that. But in any case, what you can see here is, as we're moving in this direction here, you can sort of see that the spatial frequency is getting higher. So it's going from 1 to 2 to 4. Okay? And so that just means that things are happening closer. Sort of this distance is decreasing as I go to higher spatial frequency. In this case, we have a spatial frequency both in the x direction and in the y direction. And so you can sort of see here, if you look at this spacing, these spacings stay the same. Okay? So that U0 is equal to 4. So basically that spatial frequency in the x direction stays the same. But what you notice is this spacing here, as I go like that, let me just change the color. It'll be a little easier to see. Whoops. How do I do that? So if I look at this spacing from here to here, that's got that spacing. But then here, see that spacing decreases, and here. Can you guys see that? Okay, it's decreased even more. All right? Let's change the pen tip here. be over here. Okay. And so that's represented by, you see this frequency is going from 1 to 2 to 4. So as that vertical frequency gets higher, then that spacing between those ridges gets smaller. So that's the idea behind looking at spatial frequencies. Any questions up to now? Okay. So what we're going to say is, and what we'll talk about a lot in MRI, is this notion of k-space. All right? And the idea is our image will be sort of a function of x and y. Okay? We're going to take the Fourier transform of our image, and that Fourier transform is going to be represented on an axis with kx and ky. Okay, where this is now looking at the spatial frequencies. And so basically the brightness of, at every sort of kx, ky, the brightness tells me how much of my image is represented by that spatial frequency. All right, and we'll get into that a little more. And then the idea behind MRI is that we actually acquire the data in k-space. So in MRI, this is what we actually acquire. And so then once we acquire that, we just do an inverse Fourier transform to go back and get our image. Okay, so what we'll be talking about over the next few weeks is how do we actually acquire that data in MRI. Okay. But the cool thing is that everything we're talking about, all that's very theoretical, is done every day with an MRI machine. It's always collecting sort of Fourier data. All right. So let's talk a little bit about how to think about k-space. So remember the axes are, once again, kx and ky. And so let's say I have a point out in k-space along the kx axis. Okay? So that point here might have some spacing. Let's call that delta x. All right? Now I move farther out in k-space. Here, you can sort of see this delta x. Let's call this delta x2. This is delta x1. So clearly delta x2 is less than delta x1. So the spacing's gotten finer, right? And therefore, that corresponds to a higher spatial frequency. So for example, so we could say kx1 is equal to just 1 over delta x1, and kx2 is equal to 1 over delta x2. Okay? So what I'm representing here are sort of like the peaks, right? All right, so that's basically, so if you're looking at things along the kx axis, they correspond to stripes going left and right, or they're vertical stripes, but the variation is this way. Okay, so if you ever get confused, you can just sort of remember that if I have some kx, ky, things along this axis, I can just draw lines perpendicular to that. That's what that represents. Okay. So similarly, if I have this point here along the ky axis, it represents variations going up and down. All right. So this has some spacing. Let's call it delta y1. And as I go further out, then I have something with even smaller spacing, say delta y2, where now delta y2 is less than delta y1. All right. And then I can also have something that's off-axis. Okay. And so now this is variation both, there's both a, there's a delta x and there's a delta y, right? And so this is going to have both a kx and a ky component to it that's non-zero. Right? So this is the basic picture that's useful to keep in mind about how different parts in k-space represent different variations. Right? Yes?
Is it the brightest part? Is that the delta x is biggest in the brightest part? Or is it just closer to the
Yeah, so the brightest part represent how much sort of energy is in that, is there. So I'll show you some pictures there.
I'm just thinking about the lines, because then delta x1 is broader than delta x2.
Okay, so let's say,
Is it because of the image? Or because
right, it would mean that for this image, it would have more energy, more of the image is composed of something with these frequencies as opposed to high frequencies. And in general, for anything biological, most things that are biological, the Fourier transform falls off as you go to higher frequencies because things are generally start out fairly smooth and then you add some details. And we'll talk about what So that's a good question. We'll talk about what does the central part of k-space mean and what's the outer part of k-space mean. Okay, so today really just want to give you sort of a review of what k-space means, but that's a good question, right? Okay, so here's sort of getting at that. So this is sort of an example of what I'm doing here is I'm sort of adding on these different components. So if I start off with just this component here, and this is sort of the running sum of all the different components, and this is the, I forget what the third row is, but let's just look at the first two rows. So here, when I just start off with this component here, that's my image. Now, if I go to the second row, I add on this horizontal thing, and now the sum is shown here. Okay. And then as I add on this next thing of two stripes, now the image is getting a little more detail. I add on this diagonal, I'm starting to see something. I add on this other diagonal, I'm starting to see a little more. And then I keep adding on these different diagonal components. Okay? And as I do that, you can sort of see I'm building up my image layer by layer by layer. Right? And so that's essentially the idea behind the Fourier transform, that I can go from this, which has almost no detail, to something like this, which starts looking a little bit like a brain. Can you ask?
It's the k-space, probably, because
Oh yes, this is the k-space, right? I think so.
The low frequency content in the first image, and as we go further, the higher frequencies are increasing.
Yeah, I think that's right. Yeah, it's just the scale seems a little weird. So yeah, but this is somehow the k-space, but it looks just a little weird. So it seems like it's inverted almost. But it's a good question. It's from the reading, so maybe they explain it more there. Okay, are there any questions about this? Okay, so let's take a look at this movie. So we'll play this movie a couple times, and what you're going to see in this movie is this is going to be the k-space, and this is going to be the image. Okay, so you can start off. We start off with just sort of stuff at the center of k-space, which is very low frequencies, right? So the image looks really blurry. And then what we're going to do is we're going to add more and more information from outer parts of k-space, and you're going to see the image sort of fill in terms of detail, right? So media not found. Great. All right. I should have pre-tested this. Okay, great. So I'll put that image in the folder, and then you can look at it offline. And I'll try to play it during the course once I figure out. This wasn't a problem last year, but oh well. Okay, let's go on to this. So this is what we have here. We have images and then the k-space on the right-hand side. All right, so this is the Fourier transform, and then this is, if we inverse Fourier transform, we get to that. All right. So let's see what happens here. So in this part, let me change colors. I need to understand this a little better. Okay, so let's say we do orange. The green's probably good. Okay, so in this second here, so here in this case, I've sort of zeroed out these parts of k-space. Okay, so these parts of k-space, you remember, they correspond to edges going left to right. Okay, so you can sort of see if we zoom in on this, if you look at, like, say, this edge here, right, it's blurred out. Okay, so all the edges going left to right are pretty blurred out. Whereas if I look at this edge here, the ones going up and down, they're pretty sharp still because I've kept that information. So you can sort of see that those are because I've zeroed out these parts of k-space, I've lost that information going left to right. So you can really see it here. This area of the brain here, this is the cerebellum. It's responsible for a lot of your motor control. You can sort of see just beautiful delineation of the cerebellum here. And then here, it's basically, a lot of it's blurred out. Okay? So that's sort of trying to give you a sense of what are different parts of k-space, what information are they giving you. So let's play the game. We can play the game in a different way. Whoops. Keep. Still running. Okay, that's still running. So here what we've done is we've zeroed out these parts of k-space. Okay, so now what we're going to do is we're going to be losing the information on the edges that are going up and down. So if we zoom in on here, you can sort of see this edge now is really blurred out. Okay? Whereas these edges here, left to right, are pretty much kept intact. All right? In here, we've zeroed out all this outer part. This is all 0 now, right? So we're losing information about edges left, right, and up and down. And you can sort of see the whole image is just really blurry. Whether you're going left to right, up or down, any sort of angle, you just got a much blurrier image. All right? So that means that the center of k-space represents sort of the low frequency content, sort of the overall shape of your image. And then the outer parts of k-space are really the defined detail. So that's something to keep in mind when we're talking about when we talk about MRI, we're going to talk about how much k-space you need to acquire, and this is one of the trade-offs you're going to make. All right? So if you're okay with a blurry image, then you can just acquire a little part of k-space, but the better image you want, you have to go farther and farther out into k-space. Okay, so in this case, this is sort of interesting. Now what we've done is we've zeroed out this central part here. So all we're really keeping is the information out in these parts, right? So if you look at this image, it's basically kept the left-right edges, right? So you sort of see these edges, but if you look here, we've lost these up-down edges because we don't have that information anymore. Okay? So this is just emphasizing that these outer parts in k-space are really giving you the edge information in your image. So here's the same game. We've only kept this information here. We've zeroed out all this part in the middle. And so now if you look at this image, you've kept the up-down edges, but you've lost a lot of the right to left edges. Okay? And here, in this case, we are keeping all the edge information. So we're keeping all this information out here. And now you can sort of see that we've got both the left, right edges. And in particular, if you really zoom in on here, the cerebellum, that's pretty cool. You can sort of see all the edges of the cerebellum there, okay? Because we've kept all that outer k-space information. All right? So that's the basic idea behind k-space. Let's see, I think we have a couple more examples. So these are images that you don't hope to see, but sometimes you do see them once in a while in an MRI system where sometimes there'll just be some spikes introduced into data. And so in this case, you see this little spike here that's been introduced into the data, right? And you can tell, and then the image you see has all these stripes on it, right? So one way to think about it is, you know, anytime you have something out in k-space, if you just draw a line from the origin to it, right, and then you draw stripes perpendicular to it, that will tell you what the stripes should look like in the image. Okay, so that's sort of something to an easy thing to keep in mind if you're sort of trying to figure out what things happen. So let's take a look. Here's this spike here. If I draw a arrow to it and draw the perpendiculars, lo and behold, those are essentially the stripes that appear there. Okay? And the farther I go out into k-space, the finer those stripes will be spaced. All right? So that's not to scale, what I drew.
So delta x is, or delta whatever is based off of how far it is.
Yeah, so basically the farther I go out, so this is the origin, right? So like the axes would be like this, right? So this is kx, ky.
Is there an actual correlation between the distance, like mathematical?
Yeah, we'll go through that.
Okay.
Yeah, sure. Okay. Any questions? Okay. So here, let's actually, can you close the door and turn off the lights so it'll be easier to see this image for everyone? So we have, okay, that's great. We have 3 groups. So pair up, and yeah, that's good. Okay, so everyone can see these images, right? So A goes to this one. So that's, I've done that for you. Okay. So now I want you to take a few minutes and talk to your neighbor, and we're going to let you, so B, C, or D goes, each of those goes with 1, 2, or 3. All right? So go ahead and take a look at these images, and then talk about it for a few minutes, and then we'll reconvene. Okay? So go.
And on B at least, you don't see left to right that well, do you?
Yeah. Yeah, I think, yeah. So if you don't
See
see left
left
to
to
right, so that
then
should
we
be
could say that
for
that's
number
the
2.
that's 3.
Oh, if it's
Left to right.
left to right is there.
Yeah, it's 3. And I'm guessing C is like all blurry.
1.
Yeah.
And B should be 2.
But D has pretty good up and down, isn't it? I'm not sure though.
Is it up and down? Left to
Left to
right.
right. I have a hard time telling it. Like B or
The B and D.
if you look at the white line, these two have it. But D is definitely the best picture.
Yeah. You can see some detail.
Oh wait, hang on. Maybe I was. Oh, so if we do that, we will lose left to right. And did we say that one doesn't have much left to right? Or did we say it has?
It does not have. So
Does
up
it
and
have?
down.
Are we saying that one has more up and down than left to right?
Up and down, I think.
Okay, in that case, yeah. And then the other one is 3.
D would be then 2.
I just feel like that one has better in general.
Yeah, better in general. But
Like it's
is
better
it
up and
better
down
up and
and
down?
left and right. Yeah, we'll go with that. Because that C as just general, not
Yeah, no.
like the form, lose the form, and
So
that's
that would
the
be 1.
yeah.
Yeah. Let's see. So that's better left. I think that's right. I think B should be.
Okay, let's regroup. So of 1, 2, or 3, which one has the most information? Like if you just, yeah, 1. 1 has the most dots kept, right?
Yeah.
Okay, so then let's say B, C, or D, which one has the most detail? D, right? So 1 definitely goes with D, right? Just even if you knew nothing about Fourier transforms, right?
Yeah.
Just from sort of how much information is there.
Did you say that if the center of the or of the Fourier space keeps like the very picture of the image, and then we have detail? Because we have a lot of details, but we don't have.
Yeah, so you have details, right? You have details both left, right, and up, down in D, right? Yeah, and those edges, because they're edges, they give you a sense of what's going on. Yeah, okay. Okay, so now we've got it down to a 50-50 proposition, right? So that's always a good test-taking skill, right? You eliminate it. So let's go with B. What does B correspond to? Obviously, it's either 2 or 3, so which is it? 2. And why is it 2? Right, because we've kept the up-down edges, right? So B goes with 2, and obviously C goes with 3 because we've kept the left-right edges. Okay? And then if there's any question, you can sort of draw an arrow out to one of these and then just realize it's going to, the perpendicular to that arrow is going to have those edges.
So
All right.
can you explain how you see like left to like the edges from left to right, up and down?
Okay, so basically it's like for example, this is left to right, right? This is edges going this way, but they're vertical
Yeah.
lines, but they vary left to right.
Yeah. So
Yeah.
How do you?
Oh, how do I, in which one, B?
Yeah.
Okay, B is, if I zoom in on B, I really see these edges, right? Right, I really see those, right? Whereas C, they're gone in C. Yeah. So what you want to do is, and then an interesting look at these edges here. That's kept in C. It's basically gone in B. Right. So you want to play the game where you need to look for where are their edges and what do they look like. Okay. So this should ever appear on a quiz. That's what you would do. Okay. All right. All right, here's your next set of problems. Once again, they are, now you have 3, 1, 2, 3, and you want to match them with A, B, and C. And once again, get in groups of 2 or 3 and discuss this and figure out what goes with what. Okay?
Yes, the C is that way.
Oh, no,
Yeah,
that
not to one, right? I was confusing it last time because I thought we were blacking out the edges, but we're actually blacking out the middle. But now we're blacking out the edges. So if we do it that way, that's left to right.
What the one should be perfect.
One would be 3 and 2.
Because the
Two
half is
goes
only counted as
across.
right. It shouldn't be bloody in the second.
Oh,
Put a
I
point
see.
and then take.
oh yeah.
And
Yeah.
horizontal it should be perfect, which is placed in
If we go
horizontal.
up,
This
right,
right.
the line goes like
Placed in
that.
horizontal.
If we go that way, the line goes like that.
So
This
it's
goes
easy.
into
So
So I see 2.
that's good QA information. So particle has to be good. This is B. Horizontal has to be good.
right, so
Horizontal is C. Horizontal.
no, this is vertical has to be good.
Okay, let's take a look at this. So once again, let's play this game. Which of 1, 2, and 3 has the least amount of information?
A.
Or sorry, A, right? A, yes. And then which of the top ones? 3, right. So those obviously go together, right? It basically has very little information in K-space, also not such a great image, right? Okay. So how about 1? Which one goes with 1? B, okay. So there's a choice for B. Okay, why does 1 go with B? Right, because I'm keeping these left-right edges, right? I'm keeping edges like this, right? Okay, and then 2 obviously goes with C then, because I'm keeping sort of edges like that, right? Okay, so everyone okay with that? So if you sort of understand that, this is basically you're understanding K-space, all right? Okay, I think we have one more. This one's a little more challenging. Okay, so there's 4 choices on top and 4 on the bottom, but if you use the same principles you did before, you should be able to get it. Okay, so I'll give you a few minutes to talk about this.
Spikes, and they're not spikes.
Which one on the lower?
Yeah, lower.
Yeah, those are like energy in there. Yeah, so you have to take into account those lines. Yeah.
No, wait, no, it goes that way.
Yeah.
Yeah, that way. And that should be either that one or yeah, it should be right.
So for A,
Yeah.
how do you?
So we have that dot here, that's our draw a line like that. Oh wait, sorry. Oh no, that's what I mean. See that they go that way,
Right.
and the lines over the pictures
Oh,
they
I
go
see.
the other way.
So like
So it's
in
only
there.
it's only number 4 that is
This-
that way.
Okay, that's right.
Yeah, right.
Yeah, that's true. Then that would be this way, so it's would be A1. B would be 1.
Yeah. I would say so, yeah. And then
C would be this way, which is 3
yeah,
or 2.
Yeah, but then the question is like when they're different. Oh,
Different orientation.
what was the difference there?
2 and 3, so we have those lines
Oh, the
this way.
background?
Yeah. So like you see the orientation of those are different. So
Yeah,
because if you do it this way, right? You just, so you see this vertical, I think the background is also perpendicular to that spike. That energy, I think.
I'm not sure why we get so much for
It is. So here we have this direction also,
Mhm.
which means it is either
so we
CA
say
or B.
case 4
Once you have stripes like that. So this one. So the second one is C.
we said the third one was
This could be first one is
Okay, seems like people are converging. So let's see. Did anyone here ever watch Sesame Street? Okay. Wow. All right. So anyways, there used to be this thing, which one of these things is not like the other? Okay. So on the top row, they're all sort of different, but which of them does not have diagonals in it? One, right? Okay. So which one does one go with? B, right? Okay. Because that obviously has no diagonal artifact added onto it, because this can only represent stripes going this way. Okay. So now we sort of play the game. Which one of the other ones looks the most like 1? 3, right? Okay. So which one do you think 3 goes with?
C.
Yep. And in fact, if we draw this and draw, then the stripes match up, right? The direction of the stripes match up. So now we're down to 2 and 4, right? So which one do you think 2 goes with?
D.
D, right? Because if we draw this and draw the perpendiculars, the stripes are going the right way. And then once again, A goes with 4. All right? So everyone got that? Okay.
So the stripe on the background, are they related to
Yeah, so the stripes are basically because I put energy into K-space at these locations. So all I did was in MATLAB, I took the Fourier transform and just added those stripes in and then did the inverse transform. So that's how I created these images. Yeah. So in your homework, you'll be doing similar things. You'll be adding spikes into the image. I think that's what you'll be doing. And then, okay, good. Confirmation. Okay.
if the bars would be smaller, how would the background change?
If the backgrounds, that's a good question. If they would be smaller, you would still see, for example, the striping patterns. So the width of the stripes is sort of giving you, the length of the stripes is essentially giving you the background, like the left, right, up, down, sort of that overall pattern, and that would just change that.
Okay, so the background would only change.
Yeah.
Not the stripes on top of the picture.
Right. If you had just a single point, you'd certainly get stripes, right, like what we saw before. But that sort of weird sort of pattern in the back is because I made that a long thing. Yeah, because I'm getting lots of frequencies added up.
Because I feel like we're getting double things now. Like we're getting the lines.
Yeah, so you're getting both. So basically, if you look at 1 and B, that shows you the effect of adding a bar. So this thing here, right, gives you this, right? So that if that was just a single dot added there, then it'd just be stripes of one frequency. What you're seeing is stripes of many frequencies adding together, and sometimes summation, sometimes canceling out, which is why it varies over the image. Okay? Any other questions before we move on? Okay. So now we're going to spend a little bit of time going into some of the sort of the mechanics of Fourier transforms. And so the definition is actually fairly straightforward. If I have some function of g of t, I multiply it by a complex exponential, in this case e to the minus j 2 pi ft, and that is the Fourier transform of that signal. And the nice thing is, so this is the Fourier transform. I can take the inverse transform and multiply it by a similar complex exponential, which looks the same except it's got a j instead of a minus j, and that's the only difference. And that's giving me, and that allows me to recover my original signal. Okay. So the nice thing about Fourier transform is for for any signal or image we're going to be dealing with in this class, you can take the Fourier transform and you can do the inverse Fourier transform. In terms of coordinates, we'll talk about things that are both a function of time. Okay, and so in that case, like g of t, and in that case, we'll use f to represent frequency. Okay, so if t is in seconds, f would be in cycles per second or hertz, typically. All right. Spatial coordinates, we might use something like centimeters or millimeters, and then in that case, the spatial frequency is just cycles per centimeter or cycles per millimeter. You sort of can always pick the units you want. And in that case, we typically use k sub x or k sub y as our spatial frequency. All right? So that's the only difference. So when you see x and kx, you know you're in space. When you see t and f, you know you're in time. All right? That's just sort of a common thing. Just to review, this is Euler's formula, which is super useful. The main thing is e to the j theta equals cosine theta plus j sine theta. We're going to see this again in MRI. This turns out to be the actual physical picture of what's going on. Essentially, we are basically going to be mapping things on a complex plane. And a very nice way of representing things is just this e to the j theta is just this on a complex plane where the vector, this is the cosine theta, this is the sine theta. So e to the j theta is just this complex phasor going around on the unit circle. Okay? And what we'll see is when we do MRI, this is exactly what's happening in your body. All the spins are sort of going around this complex, basically complex phasors. Right? So that's that. So then when we have the 1D Fourier transform, we can apply Euler's formula. We can take this and break it into the cosine and the j sine. And so what we're getting is we're taking sort of our function g of x, multiplying it by cosine 2 pi kxx, and then we're integrating it, right? Which is basically an inner product. It's sort of saying how similar is g of x to cosine 2 pi kxx, and then also how similar is g of x to sine 2 pi kxx. And those are both the same frequency, they're just off by a phase of 90 degrees. So essentially, by doing that, we're capturing how much of my signal is in that frequency. Okay, so that's all the Fourier transform is doing. It's saying, okay, you have this signal, or you have this image. For every value of kx or kx and ky, tell me how much of the signal is in that frequency band. All right. So let's talk a little about computing transforms. So in this class, there are a few transforms we'll use over and over again. So it's useful to just go over them. All right. Those will be delta functions, rect functions, sinc functions, and cosines. That's all you really need to know. Okay, so you don't need to know other things, all right? So as long as you know those things, and also complex exponentials, because that's what cosines and sines are made of, all right? So really, and we'll go over that and review that during the course, but today we're going to sort of give you the fundamentals. So the easiest one is f of delta x. So if I put delta x into this integral, what property do I use here of the delta function to get this integral? The area is 1, but I'm also using the sifting property, right? Because it only picks out the value of this thing at 0, and this at 0 is equal to 1, right? So then basically it's sifting out the value of this at 1, which is just 1. Okay? Similarly, I can do f delta x minus x, and so now this is going to sift out the value of this at x minus x naught, and so at x naught, right? And so that gives me e to the minus j 2 pi kx x naught. Okay, so this uses the sifting property of the delta function. All right. The rect function is super useful, and just as a reminder, it's this function. It goes from minus a half to a half and has a value of 1. Okay. So that's easy to integrate because I can just put the limits of integration there, minus half to half. It's 1, so there's nothing there, and it's just multiplying this. That's just exponential, which we can integrate. And when we do that, we get sinc of kx, or it's sine pi kx over pi kx, okay? Which is so useful that it has a name, sinc kx. And what that looks like is this. So it has a value of 1 at the origin, and then it has its zeros at all the integer values. Okay, so that's useful to keep in mind. All right. And this is really interesting because if you we use this all the time in MRI. We basically, if you look at an oscilloscope in terms of what sort of pulses we put into the MRI system, a lot of them are sinc pulses. Okay, and in fact, when you look at the code that goes behind the MRI machines, you see the word sinc a lot. So it is actually used all the time. All right. Any questions before we move on? Okay. Okay. How about this one? Anyone want to take a gander at computing this one? Let's try. Okay. So how do we integrate an exponential? So this is like the form e to the ax, right? So what's the integral of e to the ax? 1 over a e to the ax, right? Okay, so let's do this. So this is going to be e to the minus j 2 pi kxx over minus j 2 pi kx from minus infinity to infinity, right? Okay, so that's easy. We can just plug in that. So that's just e to the minus j 2 pi kx at infinity, right? Minus e to the minus j 2 pi kx at infinity over this minus j 2 pi kx. Okay, so what does this equal? What's e to the minus j 2 pi kx times infinity? 0. And what's e to the minus j 2 pi x? Oh, this is at minus infinity. What's that? Okay, so we said that this goes to 0. What does this go to? This goes to infinity? Okay. So we have infinity, right? So does everyone agree with that? Or what have we missed in the logic? The what? Well, yes, but what is really interesting about e to the minus j 2 pi kx? So remember, yeah, so remember e to the minus j 2 pi, e to the minus, that has the form e to the minus j theta, right? Right. So what's the magnitude of that e to the minus j theta? The magnitude is always equal to 1, right? So this is simply a vector that has some angle theta, or minus theta in this case. Let's make this e to the j theta. Right, so anytime you see e to the j something, it just has a magnitude of 1. And all this infinity thing is doing is changing the phase, right? So basically it's not defined, right? We don't really know what e to the minus j infinity is, or e to the j infinity is, right? Because it's just that infinity is just the phase term, which is just going around and around and around. So the problem is this doesn't really work. Okay? So I just did this just to show you. Now, it turns out that the answer is you have to get into what are generalized functions. And it turns out that the Fourier transform of 1 is just delta kx. And you can go through the proof here. This is under the concept of generalized functions. But for the purpose of this class, you just have to know that delta of x goes to 1, and 1 goes to delta of kx. Okay? So that's easy to remember. So deltas go to 1, 1s go to deltas. All right? So just that's all you need to know. If anyone wants to get more details on why we do all this, I'm happy to talk with you offline. All right? Okay, any questions before we move on? Okay. So so this is definitely one pair to remember. Delta is going to 1, 1 going to delta x. And similarly, if I take e to the j 2 pi k naught x, it's going to give me delta kx minus k naught. And this is really useful to remember because we do this, this comes up a lot. So the way to remember this is telling my frequencies at k naught. Okay? And so what it's saying is if my frequency is at k naught, then probably a good representation in kx space is I just have a delta function at k naught. So that's how to remember that. Okay. Similarly, cosines and sines can be written as sums of the complex exponentials, right? So this is like e to the j 2 pi k naught x plus e to the minus j 2 pi k x naught x over 2, right? So therefore, and these are useful to remember. So a cosine will always give you, this is the frequency, k naught. So it's going to have 1 at k naught and 1 at minus k naught, and it's going to have 1/2 and a half. All right? So it's useful to remember that cosines go to 2 delta functions and sines also go to 2 delta functions. It's just that then it's going to be 1/2 minus 1/2, and this is 1 over 2j minus 1 over 2j, I guess. All right. Okay, so one thing to remember is this thing called duality. We've already seen this already in this case because we saw delta goes to 1 and 1 goes to delta kx, right? So it means if you know how things go one way, you sort of have a clue as to how things go the other way. So that's a nice thing about the Fourier transform. So for example, I know that e to the j 2 pi ax goes to delta kx minus a, okay? That's because here, see this frequency there's a, and so this just goes to something that has a. And then delta x minus a, from the shifting theorem, we go to e to the minus j 2 pi kx of a. So here we're seeing a complex exponential going to a shifted delta function. We're seeing a shifted delta function going to a complex exponential. There is this sort of difference in minus signs there. Okay? And so the specific case of duality is the Fourier transform of g of x equals g of minus kx. All right? And we'll do one example of that. That is very useful. So what's the Fourier transform of sinc of x? Okay, remember sinc of x was this funny looking function, right? Yes, it equals the rect. But I just want to point out to you that the other thing you could do is you could take sine pi x over pi x and multiply it by this and integrate that, right? And that would take you a little bit of time, right? You'd have to do I don't know what you would do. It's the integrating, like u, v, you know, what is the integrating a sum? Integrating by parts, right? Okay. So you could do that and maybe you'd be done, but it's much faster to just duality and say, okay, we know that the transform of rect goes to sinc, therefore the transform of sinc goes to rect of minus kx, but rect is symmetric, so it just goes to the rect function. So that's the other thing to remember. Rect goes to sinc, and sinc goes to rect. Okay, so that will come up quite a bit, and so that's useful just to commit to memory that rect goes to sinc and sinc goes to rect. Yes?
For the homework, though, we're supposed to be actually doing the actual derivation math to get to that, right?
Was there something in the homework that, this homework you mean,
I
or?
think the homework asked us to derive a couple of rect functions.
The homework 4 or homework 3?
Homework 4.
Okay. Homework 4, there's like 4 problems in part 1, and we'll go over one of them later. So you don't have to do any derivations.
Oh, okay.
Yeah.
Cool.
It should just be applying the properties.
Okay.
Okay. Let's talk a little bit about 2D Fourier transforms. So 2D, just the main thing is now we've got double integrand, and then we've got kx and ky. We're integrating over dx and dy. And then for the inverse transform, same form, but instead of a minus j, it's a plus j. Okay? And notice, once again, Princeton Links uses u and v, but the standard in the field is really kx and ky. So we'll kx and ky. All right? So here's getting at the question we had before, which is how do we think about these complex exponentials, right? Once again, we can write them as a cosine plus a sine. And so we just really need to think about what does a cosine of 2 pi kxx plus ky look like. Okay? So let's say in this case, ky is equal to 0. Right? So now I just have cosine 2 pi kxx. So this is just a function of x now, right? And this has spacing of 1 over kx, so that's the period of this cosine, right? And this is where we get those stripes going left to right, okay? Because that's how I would represent my function cosine 2 pi kxx. It's just a cosine that varies with x, right? Here, ky equals 0, right? Or kx equals 0 here. So now we just have cosine 2 pi kyy. This is just a function that varies with y, right? And it has spacing 1 over ky. And then if I have cosine 2 pi kxx plus kyy, then this is going to vary both in x and y, and the spacing is given by this, 1 over square root of kx squared plus ky squared. All right? So the next slide goes through the math on that, but let me give you a simpler way to remember this. Okay? So remember in k-space, let's say we're at some point kx, ky, right? So what's the magnitude of that line? Yeah, just square root kx squared plus ky squared, right? So this point here has a spatial frequency of 1 over that, spatial spacing of 1 over that, kx squared plus ky squared. Okay, so that's how that works. And then the other thing we know is that this theta here, so that theta here is the arctangent of ky over kx, right? And that's exactly this angle here that you're going to get. So for example, remember I said if I'm out at some space in kx and ky, I can draw this line and then draw the perpendiculars. Right? That's exactly this picture here that we have here. Okay. So this is sort of the geometry of it here, but in terms of thinking about it, if you just sort of remember this picture here, that should get you basically what you need. Okay. So for any position you are in kx and ky, now you can tell me, you can just sort of see, so you can sort of see as I go farther and farther out in k-space, that square root of kx squared plus ky squared is going to get bigger, right? So 1 over that is going to get smaller, so it's much finer. And then the theta, what angle it's at, is just given by the arctan ky over kx. Okay. All right, any questions before we move on? Okay, so then what the Fourier transform is doing is essentially now we take our object. For now, we just imagine multiplying it by, let's say, a cosine or a sine. Okay. Later on, we'll talk about multiplying it by complex phasors, not today, but in a future lecture. And then we integrate it over all of space. So that's integrated by this d volume. Okay. And then when we do that, we put the value in here into our Fourier transform. And then we can go to some other place in k-space, and here's my object. I multiply it by some pattern, I integrate, and then I take the data and store it there. So when we get to MRI, this is essentially what we're going to be doing. Over time, we're like filling in k-space bit by bit by bit. Okay? And so the next couple of weeks is going to be explaining how do we actually do that. Okay? But it has a little more meaning if you understand what k-space is. Okay? Any questions? All right. Okay, so let's talk about a few more things, properties. So one super useful thing is separable functions. So if g of x, y can be written as a function of x and y, then it turns out that the Fourier transforms is easy to do. It's just the Fourier transform of the x part and the Fourier transform of the y part. Okay, so that's really useful. So for example, if I have rect of x times rect of y, the answer is just sinc of kx, sinc of ky. Okay. Now do not make the mistake. This is not so if I have rect of x, okay, that does not go to sinc kx, sinc kx. That's not true. Okay, because these are the same variable. All right. So for that, we need another thing. We need another theorem that we'll do later on. But this is a common mistake that people make, so I'm just telling you, don't make that mistake. Okay? If they're different variables, then you can apply this. If it's the same variable, then you can't apply this. Okay? Don't make this mistake. All right, that's your warning. Okay. So this is an example. So this is my rect of x times rect of y. So this will come up a lot. We'll use this a lot because we use this basically to represent how much k-space we're going to acquire. Okay, and it turns out the Fourier transform of it is just sinc of kx times sinc of ky, which is this nice looking function here. Okay. All right, so let's see how are we doing on time. Okay, let's at least talk about this problem. We'll just ask if it's separable, and then we'll let you guys do the Fourier transform on your own. So first question is, take a minute and think about this. Is this function separable? That's the question. So any guesses? It's separable? Okay. So how would I write it? I'd write it e xp minus j 2 pi 8x times e to the minus j 2 pi 9y, right? And then I would group the sign over here, right? Sine 28 pi x, right? So these are definitely separable, right? I could take the Fourier transform of this. I could take the Fourier transform of this. Okay. So let's actually go and take the Fourier transform of this side. So just to give you an example of what we might do. So e to the minus j 2 pi 9y. So what frequency is that at? What's the frequency of that, the complex exponential? So this has a ky of what? 9, almost. It's minus 9. Yeah, so the kx is minus 9. Okay, so what this is going to look like is along the ky axis, I will have a delta function at minus 9. Okay, and that would be written as delta ky plus or minus 9. Which would it be? Plus 9, right? So that's the Fourier transform of that part. Now let's look at this one. So how would I figure out the Fourier transform of this thing? What would be, given that, like, just from, if you didn't know any other properties, how would you get this into a form that you could work with? What can you do with the sine function? Right, you write it as sum of exponentials, right? It's e to the plus j 28 pi x minus e to the minus j 28 pi x over 2j, right? And then I can multiply this by that. And then I can just add, I can do the things, and then I'm going to get complex exponentials, which I can then take the Fourier transforms of, right? Okay, so that's how you would do that problem. All right. Here's some examples of separable functions. Delta xy is equal to delta x times delta y. This goes to 1, this goes to 1, and so the multiplication of those two goes to 1. Here's an interesting one. Delta x is equal to delta of x times 1, right? Delta of x goes to 1, and 1 goes to delta of ky. So the answer is delta ky. All right. So if something is defined as a function of x, you only see an x there, it just means the function of y is just 1. Okay, so you have to put in a 1 there. Right. Another really important thing is the center of k-space, which we've sort of hinted at before, which is we said that the central parts of k-space are just sort of like the low-res image. Okay, turns out the center of k-space is really important. That's sort of like the mean value, and so you can sort of see if I put in a 0 here, then this just goes to 1, right? So I'm just integrating my function g of x over all of space, or in this case, g of xy over all of space. So that's basically the area under the curve, which is related to the mean value of your image. Okay, so that's why the center of k-space typically is, when we're trying to maximize things, we're always saying, did you really maximize the center of k-space, because that's the overall brightness of your image. Okay, so you have this image, there's a lot of detail on it, but if the overall mean value is not optimized, you're not going to do a very good job of having a good image, right? Okay, another thing that will come in useful is that the Fourier transform is linear, which just means if I have a of gx plus b of hx, I can write the Fourier transform as the sum of those Fourier transforms multiplied by the scalar values. Right? So that's a good thing. Linearity is always good. Let's do one example of that, which is this, is that here's 1 plus e to the minus j 2 pi ax. So the 1 goes to my delta function of kx, ky, and then this one goes to, this is sort of implicitly multiplied by 1, so this gives me this delta function, and the 1 gives me this delta function. Okay? So here we're just showing that if you have two things added together, you can take the Fourier transform of the added things, okay, or the addition of the Fourier transforms. Probably one of the most useful and the one that you'll use the most is the scaling theorem. Okay, it just means if I have g of ax, then the Fourier transform is 1 over. This is what you've derived on homework 3, I believe. So you should be fairly familiar with this. And the idea is here I have rect of x, and then I go rect of 3x. So I've sort of squeezed it, right? And then in the Fourier domain, I have sinc of kx, and now by applying this, I have 1/3 sinc kx over 3, so now I've dilated it and squeezed it down, okay? And so this is this sort of duality that we always have, this is the uncertainty principle, whereas you go squeeze things in one domain, they get broader in the other domain. Okay, so these are basically, I think you might have already seen this on the exam, or this is sort of what we provide on the exam. So this basically gives you a lot of the different Fourier transform pairs, at least in 1D, some useful facts and definitions. This is from the book, similar things here. Okay. So one concept that we've talked about that you've heard in lecture is this thing of the modulation transfer function. And so essentially, this is when we take the impulse response. So these are all impulse responses. So in general, we might have like h of x, and then the modulate transfer function will denote h of kx. Okay? And so here, once again, we see the scaling theorem where as we get broader in one domain, we get narrower in the other domain. Right? The main thing here for today, though, is that we're saying that for every function, we can either look at its impulse response or we can look at its frequency response. Right? Because we can always take the Fourier transform of its impulse response, assuming it's a nice function. Okay. So now what we want to do is look at that and see what implications that has for thinking about how to look at these systems. And here's the thing. We talked about last time in the supplementary lecture about how if I have a linear time invariant system, right, which has some impulse response h of x, and I have an input g of x, right, the output can be written as g of x convolve with h of x, right, if this is a linear shift invariant system. Okay. So now the question is, what is the Fourier transform of that, right? I'd like to know what's the Fourier transform of my output of my system. So that's the motivation. It turns out that the answer is simply, if I have this convolution here, it's a multiplication of that. Okay? So this is convolution going to multiplication. This is convolve, and this is multiply. Okay? And I can have a dual. I can have a, if I multiply, then I convolve. And this is getting at the thing I was talking about separability before, right? If these were x and y, then this would be a multiplication, right? But this is x and x, so therefore the multiply goes to convolution. So that's the thing to remember. Okay. So let me just give you some sort of intuition as to why this is the case, and then we'll sort of keep going. And I think I want to leave a little bit of time just to go over one or two problems in the homework, okay? Just to sort of set you up on those. So this is some function g of t, right? Which we can write as a sum of these sinusoids, right? And therefore, we can represent, let's say this is A1, A2, A3. Those are the amplitudes. So we can always think about the Fourier transform of that signal as well, right? So that's basically just Fourier decomposition. And now we say we're going to put this signal, g of t, through my system, h of t, which has this. This is its impulse response. Okay? And then we can always take the Fourier transform of this, right? And that's my frequency response. So that's the frequency response of my system. So we know from before that the output y of t is just going to be g of t convolved with h of t. Okay? But I can also think about taking each of these sinusoids and multiplying it by this frequency response. Right? So I could take this and multiply that, because this tells me how much each of those sinusoids gets either gets attenuated. So I could do that, okay? And then if I sum those up, the summation of all these, right, should also give me my output. And so that is just taking each of these guys and multiplying it by its, particular value here, and that's g of f, y of f, or g of f, h of f. And so that's basically the intuition behind that. That because I can break things into sinusoids, and if I know how much each sinusoid is weighted by my system, then that's a multiplication. And that, therefore, the Fourier transform of my convolution should just be equal to this expression here. Question?
Just to hear, or make sure I'm following.
Yeah.
So when you're putting the amplitudes down there, it's
Yeah.
frequency, and that's the frequency of the sinusoid.
Sorry, the frequencies are F1, F2, F3.
And that's of the ones with.
Yeah, so this A1, A2, and A3 would be the amplitudes.
Yeah.
And so let's say this is F1, F2, F3.
And then frequencies put in there.
Yeah, and then this would be like H1, H2, H3.
And that's the Fourier.
Yeah.
H. Okay.
So for example, I take A1 times H1, A2 times H2, A3 times H3. Right? So so you think about frequency response is telling you how much is that what does that frequency get multiplied by? Okay? So if you think about it this way, it sort of makes sense, right? And that gives you this, yes. So you can sort of see here that I started off with A1, A2, A3, and now these, like this value here, got more attenuated than this value, right? So that sort of shrunk it down. Okay. Okay, so I'm not going to go through this, but this just sort of talks about the math, about why this makes sense. Also, another thing is that these are sort of eigenfunctions, and so you can read that at your own pace. It's not critical to understanding the theorem. Okay. So let's talk more about applying this convolution theorem. Okay. So let's say I have a function, the triangle function, which looks like this, 1 minus absolute value of x. Okay. So you could all sit down and figure out this integral, but it would take you a little bit of time, right? Once again, you have an x and e to the minus j 2 pi x, so you have to do like integration by parts, right? Okay. So you could figure that out, but it turns out this function here is just the convolution of two rect functions. So I can just by inspection, I know this goes to a sinc, and I know this goes to a sinc, and therefore the output, just the Fourier transform of the convolution, must just be the product of those two sincs. And so I just get sinc squared kx. All right, so that's useful to know. So once again, you can do this in 2D as well. So convolution in 2D just leads to multiplication, and multiplication leads to convolution. All right. So here's an example of this convolution example. So here I have my object, and I'm convolving it with this impulse response. Okay, and so you can sort of see here that this object here looks blurry, right? Okay, so now let's see what's going on in the Fourier domain. Here's the Fourier transform of my object. This is a sinc function here, right? So it goes to a rect function in the Fourier domain, right, which looks like this here. And this is just keeping values in the center of k-space. Right? So when I multiply here, I'm doing a multiplication here, it's only keeping that part of k-space. Okay, so this was a convolution here, and there's a multiplication here. And so this sort of makes sense, because remember, when we only kept the center of k-space, things got blurrier. Okay, so this is something we'll do quite a lot. In MRI, we use the rect function, this rect function here, to say how much of k-space I'm keeping. Right? So I take my full k-space, I multiply by some rect function, and this tells me what I've acquired. And then the inverse Fourier transform of that is my image. So obviously, the bigger I make that rect function, the more data I'm keeping, and then this image should get better and better. All right? So that's the motivation behind why we do all this. I'm going to skip over this one, but it's just convolution of multiple parts, multiple systems together. You can just multiply their frequency responses by each other. And so that just means if I have a system that has, say, 3 frequency responses, A, B, and C, then it's the multiplication of the 3 that gives me the overall system response. Okay. So one question you could ask is, if all these systems cost the same, A, B, and C, which one should you upgrade? Okay. So one thing is we could upgrade C. Okay. Let's say I spent $10 to upgrade C. Would that really change this very much? Okay. So which would have a bigger effect on this overall product? If I had like $100, let's say systems cost $100. I spend my $100. A, right. Make A better, it's going to have the most effect, because A is my limiting factor here. A is the narrowest, so that's like the narrowest thing. So if I can make that broader, then that's where I should spend my money. Okay, so that's one way. That's one instance where sort of understanding that it's the multiplication of all these frequency responses gives you the right answer. Okay. Modulation is here where we are taking one function and multiplying by the other. So modulation is also just a fancy term for multiplication. And in this case, we took our function, we multiply by complex exponential, so then we convolve it with, in this case, a shifted Dirac delta function, and that just shifts my function over k-space. Okay, and same with cosine and sine. Does anyone here know what AM radio is? Anyone heard of AM radio? Yeah, amplitude modulation. So you can still get it on your car, right? I mean, you can still get AM radio. Okay. So all AM radio is doing is it's taking your sound wave and multiplying it by some cosine, typically 100 kilohertz or something like that. Okay. And so that it can be at a frequency that you can broadcast. Okay. And so what that does, if this is the Fourier transform of, say, your speech waveform, it's just taking that Fourier transform and shifting it up to a higher frequency. Okay, so that's all it's doing. Does anyone know why you need to do this? Why do you have to? Why can't you just broadcast your voice with an antenna?
It gets attenuated over long distance.
Right. Well, I mean, obviously, if it's audio, right, there's acoustic will die off. But why can't I just convert so this is already electrical, let's say, right? This is electrical. So why can't I just take the electrical version of my voice and hook it up to an antenna and broadcast it? Be distorted, possibly, but there's a more fundamental reason. Anyone?
We have a concept of carrier frequency.
Carrier. So why do we need high carrier frequency? That's getting at it. So this frequency here is the carrier frequency. The what?
To transmit over a long distance, we need a high frequency.
That's not necessarily true.
Range of, say, radio waves.
Yeah.
So to meet that, the frequency of ours may be lower. So we sort of use the radio wave band as the carrier frequency, and then superimpose this and maybe.
Let me ask the question. That's getting at it. So let me ask the question differently. Do do you guys remember the relationship between frequency and wavelength? So if I have a very low frequency, is the wavelength big or small? Big, right? So it means if I have a very low frequency, I need a really big antenna, right? And then, so if I have a higher frequency, then my antenna can be less, okay? So that sort of is one thing where basically you can't have an antenna that's at that low of a frequency because it would be like as big as San Diego or something, or from here to like, you know, I'm not sure how big it would be, but it wouldn't be that big actually. I mean, but it would be just, it's bigger than is necessary. So so that's why there's this trade-off between, you know, that's why we're trying to, one of the reasons why we're trying to get it into a higher frequency, so we can actually, it's actually practical to radiate it electromagnetically. It'll turn out that the wavelength we're talking about for MRI turned out to be about this big. Okay, so okay. So, anyways, in terms of imaging, here's an example where here's the object. I multiplied by a pattern of bars, and I get this sort of bar pattern delineated by the rect function. The rect goes to a sinc. This 2 bars, you can't really see that there should be like 2 little dots there. And then basically, then this is convolution. So in the Fourier domain, I just have these 2 shifted sinc functions. Okay. All right, so let's talk a little bit about the homework. So, so these are all just things where you would applying these different things, and basically all you really need to do is so let's take for example A. So what would you need to apply? So I have rect of x over 10 cosine 2 pi of x, right? Okay. So what would be the first thing you do? So what's the Fourier transform of the rect of x over 10? Right? And then what's the Fourier transform of the cosine 2 pi x? Sum of delta functions, so 1/2 delta of kx minus what? What's the frequency of that? 1, right? So implicitly, this is kx equals 1, right? Because it's always of the form 2 pi kxx, right? So kx is 1, so this is minus 1, right? Okay. So now here comes the question, what do I do with those 2 things? I multiply them too. Okay. So are we done yet? So what does this equal?
So kx equals to.
Yeah, so let's draw it out. So this I'm just doing this because we're not done yet, right? There's a simpler way to write this, okay? So let's just draw what sinc 10kx looks like. We can forget about the leading factors, right? So sinc 10kx looks like what? Where does it have its zeros? Where is its first zero?
1 minus 1.
Where?
At 1 we have the first 0.
Right, so sinc kx would have its first zero at 1. Where does sinc 10kx have its first zero? 1 over 10, right? So this is 1 over 10, 2 over 10, all the multiples of 10, including 1, right? Okay, so it's got zeros all those places. I can't really draw it. Okay, all right. So we know it's 0. So we know that sinc. So we know that sinc of 10 kx at kx equals 1 just equals sinc of 10, which equals 0, right? We know there's a 0 at 1, right? Okay. Where does this delta function have its values? So this is kx, right? So I have a delta function where at 1 and another one at minus 1, right? Okay. So what's a 0 times a delta function is what? 0. So the answer is 0. Okay. So the idea behind doing this is I think all these problems, it's been a while since I wrote these problems, but these problems are all designed to be like, don't just stop. So you have to graph it, and then when you graph it, you should sort of see, oh, maybe it's 0, maybe it's something else. Okay. But so basically, all these looks like they're all using scaling theorem, right? They're using the convolution theorem or convolution modulation theorem, okay? And they're also using, rect, sinc, and also cosine going to 2 delta functions. So you should be able to do B, C, and D. They're all basically variations on a theme, right? Okay. Any questions on that? So you're 25% of the way there on that problem. Okay. And then the last thing is the shift theorem, which is basically if I have any shifted function like g of x minus a or g of x minus a, g of y minus b, if I just have something and I just shift it, the frequency content really hasn't changed, right? I mean, it just has the same frequencies in it, but the phase information will change. So the phase tells you sort of where things are, and that's given by this shift theorem. So this shifting can be represented as g of x convolved with a shifted Dirac delta function. So I can use a convolution theorem. So I know g of x gives me g of kx, and then this gives me the complex exponential. So it's just basically my original Fourier transform multiplied by a complex exponential. And one thing you can sort of see is that let's look at the magnitude of that. So g of kx e to the minus j 2 pi a kx. What's the magnitude of that function? Right, just g of kx, right? So it doesn't change the magnitude of my function. Okay, because the magnitude of this guy is always 1, right? So you remember, you can always take AB equals AB, right? So that's all we're doing. Okay. So that makes sense because the magnitude sort of tells me how much energy is at each frequency. The overall Fourier transform has this thing called a phase term, which it's hard to think about, but basically it just is a term that tells you where are you in space, and it just tells you have you shifted yourself. All right. So I think we're now at the end. So we have a few more minutes if you have additional questions, but the last 2 slides are really just summing up the properties. So this is some of your basic properties that you can use that we've gone over, and this is the same thing from the book with some additional ones. All right, so before we end, are there any questions? Okay, so that's great.